In this video, our goal is to provide an effective understanding of control loops for new teams. But firstly, what is a control loop? In short, a control loop is a piece of code that uses a sensor in order to maintain a velocity or a position value or something of that nature to a specific point. But why would we want to do this? Now, if only I had a field that I could show you on. Oh, well, that works. Now let's say you made an autonomous program to drive forward and to turn to face the cube. Now you've tested this program and it works well. But now your power in your robot is higher than it was before, and it actually causes you to overturn. Even if you're using sensors, the drift on your robot will still cause you to overturn, as velocity will still play a factor into the overall momentum of your robot. However, if you had used a control loop, you would be able to be at the value that you desired to be at, and the robot's code would actively work to keep you at that position or velocity. Before we get into the logistics of a control loop, first we need to talk about what sensors you can use for a control loop. To determine which sensor you should use for your control loop, you really need to determine what it can send back to the cortex. For instance, if it can only send back a binary value, like a 1 or a 0, you probably should not be using it for your control loop, as it is not able to show you a position or a velocity or an angle or any other type of piece of information like that. However, if you have something similar to a gyro or a sonar that can determine your position, angle, or rate of movement, then you certainly should use that for your control loop. When picking a sensor for a speed control loop, you need to consider its accuracy and its relevancy. For instance, for accuracy, a potentiometer receives 4,096 different possible data points for its position, while an encoder, over that 270 degrees, would only receive 270 different possible data points, and thus you would choose the potentiometer as it is more accurate. In regards to relevancy, you need to pick a sensor that is made to determine that type of data. For instance, you would not use a sonar to determine how far you have turned, as you would probably use a gyro for that. Most control loops in both VEX and the world today use something that is called PID control. A PID loop is comprised of three constants: proportional, integral, and derivative, each with their own functionality and use. As a precursor, the current value and target value variables in the pseudocode represent values that are coming from the sensor that you have chosen based on what we have stated before. While we explain each constant of this code, we will show how the PID graph will look with that constant, as well as the ones preceding it. The proportional constant works to create a speed inversely proportional to the amount of error present. The integral constant works to accommodate for varying loads by adding a value proportional to the accumulated error to the speed. The derivative constant uses the rate of change for the error in order to manipulate the speed value accordingly. In total, this control loop helps you to maintain a consistent velocity or reach a consistent position. And this helps extremely during autonomous, as you can try to reach a consistent angle or reach a consistent position with your lift, or try to maintain a consistent velocity with your drive. Thank you for watching. We hope that this has provided you with an introduction to control loops that you can practically apply to your robot.